In 6.3, we're going to start talking about integration by parts. And integration by parts is a strategy that helps us sort of tie the product rule of differentiation into integration. So when we have a product of two functions and we're integrating that product, but regular U substitution doesn't help us here. So for example, if you look at this problem right here, I have a product. I have e to the x times x, and I can't integrate this using U substitution in a way that we know how to do as of right now. So there has to be a way to integrate something like this, which doesn't really seem to be all that complicated of a function. So what we're going to do first is we're going to derive this idea of integration by parts by first analyzing the product rule. So we're going to look at the product rule for derivatives to help us derive integration by parts, because you could sort of think of integration by parts as the inverse of the product rule. So let's go ahead and derive this. This is just going to be f prime of x, g of x, plus f of x times g prime of x. That's just the product rule. Now what we're going to do is we're going to tie this to integrations. What we're actually going to do is we're going to integrate both sides with respect to x, and over here that's just going to give me f of x, g of x, and for the purposes of what we're doing right now, we're going to ignore our constant of integration. Is going to equal the integral of f prime of x, g of x, dx, plus the integral of f of x, g prime of x, d of x, dx. And now what we want to do is, our ultimate goal was to have the product of two functions, the integral of the product of two functions, on one side of this equation. So let's go ahead and subtract. Let's subtract this integral on both sides. And I'm going to rewrite it so that this guy is on the left. So the integral of f of x, g prime of x, dx is equal to f of x, g of x, minus the integral of f prime of x, g of x, dx. And this is integration by parts, and it might not really seem like we did anything incredibly valuable here, but what we did was we said if we have the integral of a product of two things, we can create a relationship where we actually are saying one of them is a function and one of them is a derivative, and we can identify those parts to be able to integrate using this method over here. So this is the derivation of it. Let's actually see how it is put into practice now. How do we use this? How is this helpful? It looks like we took something and made it more complicated, but let's see how we actually have created something that in certain circumstances is really going to help us integrate something that we otherwise do not know how to integrate. So most commonly when you see integration by parts, you're going to see it written in terms of u and v. We just did it in terms of functions, so I'm not going to reproduce this proof that we basically just did. I'm just going to point out that it says the integral of u times v prime dx is equal to uv minus the integral of v u prime dx. Or more commonly, you're going to see it this way. The integral of u dv is equal to uv minus the integral of v du. And this is often referred to as sort of an acronym to help you remember as ultraviolet voodoo, to help you remember the order. You're saying u times v minus the integral of v du. So ultraviolet voodoo is just one of those little mnemonics that someone came up with to sort of help you remember integration by parts. So how do we do this? How do we use this? Anytime you're doing an integration by parts problem, meaning you're starting the problem, you're checking all the things that we have already learned about integration. Can I divide? Can I simplify? Can I use the power rule? Can I use U substitution? You're walking through all of those things that we have been learning all year and getting to the point where no, we can't use any of those things that we have learned. So what you are going to do is you are going to define u to be the part of the integrand, which is x e to the x in this case, the part of the integrand whose derivative is simpler than itself. Let u be the part of the integrand whose derivative is simpler than itself. In this case, that's x. The derivative of x is 1. The derivative of e to the x is e to the x, so that isn't really going to help me. That's not simpler. So the u is going to be defined as x, because x is, when I take the derivative of x, I get something simpler, which means that dv, right, because we're saying this integral is u dv, dv is going to be defined as everything else, e to the x dx. Something important to note, dv needs to be the most complicated part of the integral, including dx, that can easily be integrated. You must be able to integrate the thing that you are defining as dv. If you can't integrate it, it can't be dv. So the very first thing you're going to do is you're going to identify u, you're going to identify dv. Then, thinking about ultraviolet voodoo, we also need to know what du is. Du, in this case, is just going to be 1 dx. And we need to integrate dv to figure out what v is. And you don't need to have a constant of integration here. V, in this case, is just going to be e to the x, because the integral of e to the x is e to the x. So now we're going to rewrite this. We're going to rewrite this as uv minus the integral of v du. So we can say that the integral of x e to the x dx is equal to u, which is x, times v, which is e to the x, minus the integral of v, which is e to the x, du, which is just 1 dx. Well, this, we do know how to simplify. X e to the x is just going to stay exactly the same. That's just a product. The integral of e to the x dx is e to the x plus c. And now I was able to integrate, using this strategy, integration by parts, an expression or a function that I could not integrate before. Integration by parts takes practice. You need to make sure that you are defining u and dv correctly. Sometimes it doesn't matter, but most of the time it's going to make a huge difference which one you define which way. So we're actually going to next just analyze a bunch of integration problems and decide an approach. We are not going to actually evaluate these integrals. So up here are a couple frequently seen integration by parts type problems. So often you'll see something like x minus some c value to the power of n times e to the ax. That's sort of something that's going to tell you to integrate by parts, or sine or cosine times something to the power of n. Or seeing natural log. Natural log is something that we do not know how to integrate. We know that the derivative of natural log is 1 over x, but we don't know what the integral of natural log is. So if you see a natural log in an integration problem and U substitution doesn't work, integration by parts is probably your strategy. Similarly, we don't know how to integrate arcsine. We know how to take the derivative of arcsine, but we don't know how to integrate it. So if you're seeing arcsine or you're seeing natural log, that is an indicator that maybe if regular U substitution doesn't work, you're going to need to use integration by parts. So let's look at number 1. So remember, for all 8 of these problems, we are not actually integrating. We are not evaluating the integral, especially since we have not yet practiced one. Only one, I guess, we practiced where you fully integrated using integration by parts. So number 1, when I look at number 1, I'm thinking through regular U substitution isn't going to work. If I let U equal 2x, then du would equal 2. That doesn't help me get rid of my x squared. If I can't divide. Changing sign of 2x using the double angle property is probably not going to help me at all here. It's going to make this more complicated. So let's see if we could use integration by parts. Integration by parts. If I was going to do that, and we're not going to integrate, so it's okay that I'm going to take up a bunch of space here. Which of these two things, so I have two functions, I have x squared and I have sine of 2x. Which of them, when I differentiate it, gives me something easier to deal with? Well, that would be x squared, right? Because if I took the derivative of x squared, I would get 2x dx. Much better. And then if I let, what didn't I use? I didn't use sine of 2x dx, so dv is going to be sine of 2x dx. Which means that v, if I integrate sine of 2x dx, I would get negative 1/2 cosine of 2x. Again, you don't need your constant of integration. Let me clean this up so it fits in this box a little better. So, moving on to number 2, integration by parts is a great approach on number 1. Moving on to number 2, again, I'm going to start with all the other things that I've learned. Integration by parts is not my first go-to, so I'm going to check first to see if regular U substitution works. So if I let u equal x squared, then du would equal 2x. So that is actually going to work. Regular U sub would be a great strategy here. We could let u equal x squared, so du would equal 2x dx. So we could rewrite this integral like this, which would then simplify to be 1/2 the integral of sine of u du, which you could pretty easily integrate. Looking at number 3, U substitution is not going to work. None of my trig identities or polynomial tricks are going to work just because I have x times e to the 5x, which again is sort of like these examples up here. So let's see if we can use integration by parts. We could let u equal the function which, when we differentiate it, becomes simpler. In this case, that would be x squared. That means that du would be 2x dx. dv would be everything else, e to the 5x dx, which means that v would be 1/5 e to the 5x. So it looks like integration by parts would work here. Don't be fooled on number 4. On number 4, it looks like this could be an integration by parts problem, but always check regular U substitution first. If we let u equal 2x to the 7th, then du would be 14x to the 6th, which means we could rewrite this x to the 6th e 2x to the 7th times du over 14x to the 6th. So my x to the 6th would divide out, and then we could just integrate this. So number 4 could be done using regular U substitution. Why don't you go ahead and pause the video and see if you can figure out the best approach on 5 through 8. Then unpause the video and see how you did. And if you get stuck on one, there's a lot of natural logs in here, and we haven't talked about integration by parts as much with natural log. If you get stuck, that's okay, skip that one. Just see how many you can get through. On number 5, the first thing I'm thinking is, what happens if I use regular U substitution? If I did that, I would let u equal natural log of x. Since I need to get rid of that, I don't know how to integrate natural log. That would give me that du is 1/x dx, which would mean that du times x is dx, which means this integral would become u over 2x times du times x. So that I could integrate without using integration by parts. So this would work with regular U substitution. Number 6 won't work with regular U substitution. Since this x is not in the denominator, it won't divide out the way that it did on number 5. So we're going to use integration by parts. To use integration by parts here, we would let u, so here x would be more simplified if I took the derivative of it. However, the thing that I define to be dv has to be something I know how to integrate. So I have two functions. I have x and I have natural log of x. I only know how to integrate one of them, and that one is x. That means that I have to let u equal natural log. U has to equal natural log because I can't integrate natural log. Hence, natural log can't be dv. So du is going to be 1/x dx. dv is going to be the stuff that I haven't used yet, x dx, which means that v, the integral of x dx, is going to be x squared over 2, or 1/2 x squared. And you could then use integration by parts, which we are going to practice. Right now we're really just focusing on picking the best approach. On number 7, my first strategy, noticing that both of these are x squares, would be to divide first. or to rewrite this as the integral of x squared plus 1 minus 1, and then split your fraction in that way. Either way, however you set it up, whether you do long division or you break up your fraction in a different way, once you divide, you're going to be left with the integral of 1 minus 1 over x squared plus 1 dx, which is actually going to end up leading you to x here and tangent, arctangent here. So we're not going to finish that out because, again, that's not what this question is asking us to do. Number 8. Number 8 doesn't actually look like a product. All I see is natural log of x and dx, but we do not know how to integrate natural log of x. Therefore, we have to use some sort of integration. I can't use regular U substitution here, so I'm going to have to try and use integration by parts. If we did this, u would have to be natural log of x because I don't know how to integrate natural log of x. That means that du would be 1 over x dx. So then you kind of should be asking yourself, well, what's dv? dv is just dx, which means that v is just x. So feel free, go back, rewatch any of these problems, talking through the strategies for integrating each of these 8 problems. Now, I really want to use the rest of this video to make sure that you are perfecting the strategies for using integration by parts. So I'm going to tell you that the 6 remaining problems that we're going to do on this page are all integration by parts problems, so I'm not going to start by looking through all of the other strategies because I'm just going to tell you we are going to use integration by parts on each of these problems. I'm going to remind you that when you're defining u is something that you can take the derivative of and get something simpler. dv is something that you know how to integrate. So on number 9, the simpler function is x. The function that I know how to integrate and is more complicated is sine of 3x dx. That means that du is just dx. And v is going to be negative 1/3 cosine of 3x. So let's rewrite this using ultraviolet voodoo, uv minus v du. So uv is x times negative 1/3 cosine of 3x minus the integral of v, which is negative 1/3 cosine of 3x, times du, which is just dx. So we're going to need to do a little bit of reverse chain rule to evaluate this integral. If I did the reverse chain rule, I would need a 3 here, which means I'm going to need another 1/3 out in front. So I'm going to keep all the red part the same here. I'm going to have minus negative 1/3. So this is going to become addition. I'm also going to have 1/3 times another 1/3, which is going to give me 1/9. And the reason that I'm doing that manipulation is so that I can integrate 3 cosine of 3x dx, which would integrate to be sine of 3x plus c. I chose to reverse the chain rule there. You're obviously more than welcome to use U substitution. You just will actually have to use a different letter than U since we already defined U to be something at the beginning of this problem. And you'll see what I mean when we work on number 10. All right, number 10. I have arc sine of x and I have dx. I do not know how to integrate arc sine of x, so I'm going to let U be arc sine of x, which means that dv is just going to be dx, which means that v is x. And du is 1 over the square root of 1 minus x squared dx. So ultraviolet voodoo here, we're going to have x arc sine x when we multiply u times v, x arc sine x minus the integral of v, which is x, du, which is 1 over the square root of 1 minus x squared dx. Now, in order to evaluate this integral, I'm going to come down here and I'm going to do U substitution. In order to do U substitution on this problem, I need to choose a different letter, and since this is the second time that we're using U substitution, I'm going to use double U, haha, pun intended, W as my variable here. So I'm going to let W equal 1 minus x squared, which means that dW would equal negative 2x dx. And then I'm going to rewrite my integral. So here's my integral. These x's are going to divide out. I'm going to take this negative 1/2 out as well, so that's going to become plus 1/2 that integral. If I integrate w to the power of negative 1/2, I get 2w to the power of positive 1/2 plus c. And then I'm going to substitute back in for w and multiply 2 times 1/2 to get my final answer. And here is my final answer. All right, let's go ahead and look at 11 and 12. And you are more than welcome, if you're starting to feel confident, to pause the video and try and work through these on your own. All right, on 11, I'm going to let u equal x plus 2. I'm going to let dv equal e to the 2x dx. That means that du is dx, and v is 1/2 e to the 2x. And then I'm going to do my substitution, ultraviolet voodoo. And that brings me here. To evaluate this integral by reversing the chain rule, I need a 2 here, which means I need to put another 1/2 here. So I'm still going to have x plus 2 over 2 times e to the 2x minus negative 1 or minus 1/4, because I have 1/2 times 1/2. That's going to give me 1/4 e to the 2x plus c. Okay, on number 12, we're going to let u equal natural log of 2x. U is going to equal natural log of 2x because I do not know how to integrate natural log. That means that dv is going to be dx. So u is going to be 2 over 2x dx, which is really just dx over x. And v is just going to be x. So when I do my ultraviolet voodoo here, the integral of natural log of 2x dx is going to equal x natural log of 2x minus the integral of v, which is x, du, which is dx over x. So this is going to be the integral of 1. So this is going to just become x natural log of 2x minus x plus c. All right, last two problems. I encourage you to pause the video and work through 13 and 14 on your own, and then unpause the video and see how you did. So on 13, you have to define u as natural log of x squared plus 1 because you can't integrate that. We don't know how to integrate natural log. So you have to define u to be that, which means that dv is just dx. So then you can identify your du and your v. When you get down to the integral after you substitute everything in for integration by parts, you can do long division or you can split up that fraction and you're going to end up getting arctan. So just make sure you're paying attention to those details and don't drop off your constant of integration at the end. All right, let's look at 14. All right, this last question is a little different because there are actual bounds on the integral. So the setup is the same. U is still going to be natural log of x, which means that dv is going to be x squared. You're going to find du and v. You're going to set everything up, ultraviolet voodoo. But then along the way, you'll see in green here, I'm saying that I'm going to just evaluate the whole thing at the very end from 1 to e. And you have to indicate that. You can't lose the bounds on your integral. So in theory, you could also write this as x to the 3rd over 3 natural log of x from 1 to e. You could evaluate that earlier on in the problem. But for me, I'd rather just tack it on with giant brackets around the whole thing so that I know the very last step is that I'm going to evaluate that integral, which is the thing I'm going to do now. And there we have our answer. Remember, you do not have to find a common denominator. You do not have to make this all one giant fraction. Those are all putting you at risk for making basic algebra mistakes, which are going to take away points on your tests and on the AP test. You may leave this unsimplified. You could even leave it at this step 1 before, where I still had minus negative 1/9, and just be at less risk of making an error. So key ideas from this section: integration by parts, a method that allows us to integrate basically by reversing the product rule of differentiation. It is something that works when regular U substitution may fail us, and there's no other strategy that we have learned. But don't forget about all those strategies. Everything that we have learned up to this point for integration is still a possibility, which is why we're going to focus a lot of time on just how do we approach an integration problem start to finish. In the next video, which is still 6.3, I'm going to teach you a method that you can use to complete integration by parts that involves using a table. It is not something that is required for you to use. It is just something that may make the work go a little bit more efficiently and will get you to the same result. Looking forward to supporting you on this in class. Thanks for listening.